Welcome to today's meeting. Today we are moving on to another aspect of math play, which is the transforms. And this time we are now moving on to Laplace transforms. Laplace transforms. We have so many transforms, but today we are dealing with only the Laplace. So we are talking about Laplace transforms. You get transform a function in t domain to f domain. So we have Laplace transform of f of t is a function f of x. So you can see that here it is x, but our normal function here is t. So we are changing the t to x. So the transformation that changes the t domain to x domain. So if we are having f of t, I want to change it to the Laplace, then it changes to becomes f of x, which is equal to L, that is Laplace of f of t. Laplace of f of t. So Laplace of f of t is defined by f of x equal to integral from 0 to positive infinity of f of t here, that is the original function that you are transforming. Now you multiply it by e power negative st or expo neg st dx. F of x equal to integral from 0 to positive infinity of f of t exponential negative xt dt. So when we're using this relation or this function, it will transform the function in t to x. But here we are saying that your x, we apply it when the t is from 0 to infinity. As you can see from the limit, we have 0 to positive infinity. Okay. So that's how we can now transform a function in t domain to x domain. Now let's see how we can compute Laplace transform for any constant function. If you are having f of t equal to a, which is a constant function, how you can do that? So by going to this, we have f of x equal to integral from 0 to positive infinity of f of t exponential negative st. And now our f of t now is a. So if we go here now, it becomes Laplace of f of t equal to integral from 0 to positive infinity of a exponential negative st. So the a now multiplied by exponential negative st dt. And this one will now transform it into the x domain, that is Laplace. So since a is a constant, we can bring a out and then we integrate exponential neg st. I know how we can now integrate exponential. We differentiate the power here with respect to t, and whatever we get, we divide by the function. So whenever we differentiate neg st with respect to t, we get negative x. So therefore, we are not going to divide the whole function again by the negative x. And that will give us exponential neg st over negative x, all multiplied by a. Now you know how to evaluate the definite integral. So we are now going to substitute the limits, upper limit and lower limit inside, and we subtract lower from the upper. So coming down here, when t is infinity, the top here will grow towards 0, will change to 0. You know why? When you divide a number by a constant by any infinity, it turns to 0. So then you now have 0 here over x minus, now you put the lower limit also there, which is 0. So when you put 0 in place here becomes 1. That also becomes 1 over x. So we have negative a into bracket 0 over x minus 1 over x. And when you simplify this one, it will give us a over s. So you see that now the t has now changed to x. Therefore, Laplace of a constant a is given by a over x. A over x. Good. Now let's look at the examples. Example 1. Compute the following Laplace transforms of the following functions. Compute the Laplace transform of the following functions. I, f of t equal to 5. F of t equal to 3. And I, f of t equal to 12. So here you can see that our a is 5. Therefore, in case we are going straight to this, we can say that Laplace of 5 is equal to 5 over s. Simple. And here also becomes Laplace of 3 is equal to 3 over s. Laplace of 12 becomes 12 over s because they are all constants like a. But let's see how you can go take them through step by step way. Now Laplace of f of t is equal to integral from 0 to positive infinity of. Now you are multiplying 5 by exponential st dt. That will transform it to x. So bringing 5 out here, and when we differentiate exponential st, we get negative s as usual. Therefore, we divide the whole thing by exponential st over s. Then we evaluate the limits. So when t is infinity, you know what is going here. The whole of the numerator now becomes 0. And when t is 0, the numerator becomes 1. So we have 0 minus 1, which is same as minus 1 over x. Then you multiply by the negative 1 outside here to become negative 5 multiplied by negative 1 over x, which is 5 over x. 5 over x. So we see that we said when we are transforming f of a is the same as a over x. So now when we are transforming f of a 5, now our a is 5. So we get 5 over x. The same thing here, if we have f of 3, then a is 3. So we are not going to get 3 over x. F of 12 becomes 12 over x. But I can go through all the processes to see if you can get this one. And then this one, you are safe. Good. So now you have seen that whenever you transform Laplace of a constant, it's a constant over s. That's what we're going to get. It's the principle. Laplace of any constant is that constant over s. Good. Now let's move ahead. Let's see how we can transform a function f of t equal to exponential at. F of t equal to exponential at. But you know that our transformer is integral of exponential negative st. So we are multiplying whatever we have from function we have by the integral of exponential neg st. So we are having f of x now equal to exponential at. Now to transform it, we are Laplace of f of t equal to integral from 0 to infinity of, now this is our f of t. So exponential at, now we are multiplied by exponential negative st dt. But we can apply the indices law here. If you remember, we have a power m times a power n, where the bases are the same. Then you see that it's the same as a power. Now we add the exponents or the powers, so it becomes m plus n. So the same way we are going to apply it here. When we go here, our a now is e. Our a now is e. So the power here m now becomes our 80. The n also becomes negative st. So you can now just transform this one to become exponential in power into bracket 80 minus st. But since the t is common to them, you can bring the t out to get something like integral from 0 to infinity of exponential a minus x or t now dt. So we apply the law of integration here. With this, we cannot do our integration. We cannot integrate it easily. So we are not going to integrate exponential a minus s t dt with respect to t. So by doing so, as usual, we are not going to differentiate the power and then divide the function by the results. So if we differentiate a minus s all multiplied by t with respect to t, it becomes a minus x. Therefore, we are not going to get exponential a minus x dt all over a minus x. Then just evaluate the limits. So when t is infinity, we are not going to get 0 over a minus x. When t is 0, we are not going to get 1 over a minus x. So by simplifying this, you notice I will tend to even what? 0, because 0 over any number is 0 apart from 0 itself. And for that matter, we are not going to have it as negative 1 over a minus x. And this one will give us 1 over s minus a, where a is positive. So by simplifying this one, we are not going to have negative 1 over a minus x, and when you transform this way, it becomes 1 over x minus a. You know why? So 1 over x minus a when x is greater than a. When x is greater than a. Good. So that's how we can now transform exponential at into s domain. Let's move ahead. Now let's say we can also transform f of t equal to t. F of t equal to t. The same principle. Let's multiply the t by exponential negative st dt. And we integrate from 0 to positive infinity. So here we are not going to have, we have to apply the integration by parts here. We So it means we are now going to, we can let t now be our u and exponential neg st be our dividend. And the rule now is u v minus integral of v dt. So we have to find our v, we have to find our du, and so on and so forth, and put them into the formula. So what we do, so we are not going to get t exponential st over negative x plus 1 over s squared exponential negative st. We have done integration by parts, so we should be able to do this one. So from there we can now integrate, or we cannot evaluate the limits. So when you put the infinity inside, we are not going to get here to be 0 over x, which is 0. And when you also put, here also becomes 0. Minus, we are now also going to now evaluate the 0 also inside. And here becomes 0 here, minus, this also becomes 1. You know why here it becomes 0? Because when x is 0, here it becomes 0 times exponential 0 here. So I'll get that one to be 0. So we will get 0 over negative x, which is 0, minus, now this also becomes 1, multiplied by 1 over s squared, and to give us 1 over s squared. Therefore, when you evaluate this, it will give us 1 over x squared. So whenever you are transforming t, it will give you 1 over s squared. 1 over s squared. Take note of that. So we have done so many transformations. We can move ahead. And then as later on we solve some examples. But before then, let's continue from sinusoidal functions. How to transform sinusoidal functions. We know them: sine, cosine. So a function involves sine and cosine, we call them sinusoidal functions. We are doing that one under the Fourier series. So given f of t equal to cos at, where a is a constant, now you know how to integrate sinusoidal functions, so no problem there. So now, as usual, we are multiplying this one by the transformer, which is exponential neg st, integral from 0 to positive infinity of the t. So, but we have to transform this one into the form. Let's run apply the Euler's formula. That is exponential iat equal to cos at plus I sin at. You know when we did the complex numbers. So exponential iat equal to cos at plus I sin at. So with that you can now transform everything there. So now if I have Laplace of exponential iat, it will give me integral from 0 to infinity of exponential iat times exponential neg st dt. So with that we can now move ahead to just transform this one into what? By applying the density law here, we are going to transform it into exponential into bracket iat minus s, all multiplied by t, and then we integrate. You know how to integrate the exponential function, so I won't waste my time. So we are now going to get exponential I a minus x t all over I a minus x, as we have it here. You know why? So now if you want to evaluate this, you can do so, and we can also even rationalize to push the I from the denominator side. So before then, let's evaluate the limits. So when t is infinity, the top here becomes 0. So it becomes 0 over I a minus x. 0 over I a minus x, which is the same as 0. Now minus, we put the 0 also inside, and that will give us 1 over I a minus x. So simplify here, we are now going to get it as negative 1 over I a minus x. From this, we can now rationalize. We find the conjugate of s 1 over s minus IA. You know we have a negative sign here. So when we multiply 2, we can get factor negative out here and become s minus IA. Therefore we have 1 over s minus IA. So you can now rationalize this one by finding the conjugate of s minus IA, which is the same as s plus IA. So therefore we are not going to multiply both top and down by x plus IA. So here becomes 1 times x plus IA for the top, and down also becomes s plus IA. So when you do that, you are not going to get x plus IA over, now let me do it again for you. So we have x 1, you have x minus IA. So we are multiplying both top and down by the conjugate of the denominator, which is 1 of x plus the sign will change when the negative become positive, positive become negative. So this is, we are having negative. We are changing to positive. So plus IA over SF. So x plus I and A. Good. So with this, 1 multiply 1 by x plus IA, it will give you the same as x plus IA. Now when you multiply x minus IA by x plus IA, we get what we call the difference of two squares. We did this one under the complex numbers. So to me, you can go to where the negative is and square the two terms. But don't forget that the square of I is negative 1. So when you do so, if you are square x to give me x squared minus, now I squared is also negative 1, a squared. So it becomes x squared minus I squared a squared. I'm squaring the both sides, both terms at where the negative sign is, because we are applying the difference of two squares. A squared plus b squared, a squared minus b squared equal to a plus b, a minus b. So we have a plus b, a minus b, the same as a squared minus b squared. So here our a is x and our b is IA. So the whole of this one becomes difference of two squares. So therefore we are now squaring, we are taking where the negative is, and then we are squaring the two terms there. So I'm squaring x to get my x squared. They are also square IA to get IA all squared, and that will give me I squared a squared. But in the complex numbers, I squared is the same as negative 1. I squared equal to negative 1. So therefore my I squared here will turn this one towards positive. Therefore we are not going to have a squared, x squared plus a squared, x squared plus a squared. So when you rationalize this, we are not going to get s plus IA all over s squared plus a squared. So you cannot separate them into two fractions. Therefore, we have s over s squared plus a squared plus IA over s squared plus a squared at this. So that will give us equation 2. Now let's go back to equation 1. Equation 1 is when we transform, we apply the Euler's formula, which is exponential IAT equal to cos AT plus I sin AT. So when you compare this one to what we have just gotten in equation 2, we can see that now we have a portion with that I, and we have another term with I. So the one with that I, we can give that one to cos, and the one with I, we can give that one also to sin, because we are having exponential IAT equal to cos 8, no I here. So this one now becomes our what? The cos, which is the same as A over S squared plus A squared. Now the one with the I, you can also give that one also to what? The sign, because sign is also attached by I. So I said by comparing or by substituting 2 into 1, by substituting 2 into 1, we now have x over s squared plus a squared plus I multiplied by a over s squared plus a squared equal to cos 80 plus I sin 80, as we're doing the comparison, because this one is the same as expo I 80, and then we are now doing the substitution. So we are substituting 2 into 1. So now, as I said, if you compare, you can see now this one, no I, cos no I. So we can now see that transforming cos 80 will give you s over a squared, s squared plus a squared. Now when you compare I also to I, we can also say that transforming sin 80 will also give you a over s squared plus a squared. So by comparing, we have Laplace of cos 80 now equals to s over s squared plus a squared, and Laplace of sin 80 is also giving us a over s squared plus a squared. So this is how you can now transform the sinusoidal function into Laplace transforms. So Laplace of cos 80 is given by s over a squared, s squared plus a squared, and that of the sine also will be given as a over s squared plus a squared. Now let's look at something here. This a now is what we see here, and the same a is here for the sine, the same a is here. So watch for that. So whenever you are transforming sinusoidal function, you should be identify your a. You should be identify your a. Now let's see examples. Find the Laplace transform of the following: I sin t. Sin t. Let's look at that one first. Sin t. So it means if you compare this one to sin 80, you can see that our a here is 1. So therefore we have a is 1. I know Laplace of sin 80 is given by a over s squared plus a squared. So by using this one, now you have a to be 1. Therefore we are not going to get it as a over s squared plus a squared. So it becomes 1 over s squared plus a squared. This will go straight if you know it. So you see that we say note a equal to 1. Another example, Laplace of sin 30. So here we have a now equal to 3. For the sine is a over s squared plus a squared. So if a is 3, now we have it as 3 over s squared plus 3 squared, which will give us 3 over s squared plus 9. Now, Laplace of cos 4x. Laplace of cos 4x. So it means here too, our a is 4. But Laplace of cos becomes s over s squared plus a squared. So let's do our substitution. So if a is 4, now we have Laplace of cos 4x now becomes s over s squared plus 4 squared. And this one now will give us s over s squared plus 16. S over s squared plus 16, that's Laplace for cos. Don't forget the cos is s over s squared plus a squared. Sin is a over s squared plus a squared. So the difference between them is a and s for the numerator. Then in similar manner, Laplace of cos 2t, here our a is 2. Therefore, since it is cos, it becomes s over s squared plus 2 squared, and that will give us s over s squared plus 4. So these are not all that difficult here. All that difficult here. So let's move on to another transform. So when you are transforming sinusoidal function, it's not a big deal. Sine and cos is not a big deal. You should know the sine you show the cos, and then identify your a and do your substitution. Now, as we are moving ahead, we are going to Laplace transform of f of t equal to t power n. We have already looked at the one of f of t equal to t. It means that one, the n was 1. And we got that one to be, we got that one to be 1 over s power t. 1 over s power t. So let's see what we're going to do. We're going to get for t power n. T power n. So Laplace of t power n now becomes integral from 0 to infinity of t power n. Now we are multiplied by the transformer, which is exponential neg st dt. Exponential neg st dt. So here we have to apply the integration by parts here, because we are having t multiplied by a term with also t. So we have to apply the integration by parts. Good. So I won't waste my time here. When we go here, then we are going to get something like t power n so we have t power n multiplied by exponential st over negative x for the first part that's using. So limits are from 0 to positive infinity plus. Now we are going to integral of v du. Integral of v du. So that will give us 1 over s integral of from 0 to infinity of n t power n minus 1 exponential neg ast dt. So at 1 point. So when we evaluate, we are not going to get this, or when it's simple, we are not going to get this. So it means that I'm not going to, let's say, integrate this portion too. But see, we are still also having the same, we have to go by the same principle. But I can just bring the n out here to become n over s integral of t power negative t power n minus 1. Now exponential negative st dt. So by bringing n out, we get this. We get this. So we have n over x. N over x. Good. Now when you do the evaluation, or we simplify this one, it will give us 0 plus, you know why it's 0? 0 plus n over s. L, that's the Laplace of t power n minus 1. You should know why it's Laplace of t power n minus 1. When you go to the original function, we have Laplace of t power n. And Laplace of t power n gives us integral from 0 to infinity of t power n exponential negative st dt. So if inside here, we are also getting integral from 0 to positive infinity of t power n minus 1 exponential negative st dt, then you can now write this one as Laplace of t power n minus 1. I hope you are getting this point. When we are transforming Laplace of t power n, that will give us integral from 0 to infinity of t power n multiplied by exponential negative st dt. So when here was t power n, here was also t power n, then multiplied by exponential negative st dt. Now, instead of this integration or integrals, we are now also having a similar thing there. But now we are having exponential integral from 0 to infinity of t power n minus 1 multiplied by the same exponential s negative st dt. So to me, if I compare this one to this, if Laplace Tn will give us this, then Laplace T minus n will also give us Laplace T minus Laplace of T power n minus 1. So that's why I've now changed the whole of this one from here. I've now changed this one in the form of this. So instead of writing all this, I've now changed this one in the form of this. So if Laplace of T power n equal to integral of T power n exponential negative st dt, then Laplace of, if you're having integral of integral of T power n minus 1 multiplied by exponential negative st dt, then I can also write this one as Laplace T power n minus 1. So that's why I've made that change over there. So when we evaluated this portion, it gave us 0. The whole thing gave us 0. You should know why. Because when you put this, input infinity there, the top here now becomes 0. And when you put 0 also there, the top also becomes, because we have a t here. So the whole thing will be 0. Now plus, now we have this. And we have transformed this one also in the form of n over s, Laplace of t power minus n minus 1. So you get that one. So we are having Laplace of t power n equal to n over s into bracket Laplace of t power n minus 1. You can note or name that one equation number 1. So you can call it equation number 1. But we said don't forget this one. Know this. I have explained this one to you. So from 1 here, we can now go through the other processes. So we are now going to now transforming Laplace of t power n minus 1 also. And that will give us this as usual. It was this form that we transform it back. So this also becomes the same as integration by parts. T power n minus 1 multiplied by exponential negative st dt. So you should know our u, you should know our dividend, and then just differentiate and integrate and put them to the formula u v minus integral of v du. And that will give us t power n minus 1 all over negative s multiplied by exponential s, negative s. Then you cannot do our evaluation here. Plus, then when we go here, this also becomes n minus 1 all over s. Now integral from 0 to positive infinity of t power n minus 2 exponential negative st dt. So you see that as we move along, the power of t now keeps on reducing. So when we evaluate, this portion now will give us 0. The whole of this portion will give us 0. When we come here, we can also transform this one as Laplace. That is n minus 1 over s, Laplace of t power n minus 2. You know how we can do that? We did that one to the first one. So we have Laplace of t power n minus 2, and that will give us this. So hence we are also having now Laplace of t power n minus 1 is giving us as n minus 1 over s multiplied by Laplace of t power n minus 2, and that's why it's equation number 2. We have got equation 1, we are now having 2 here. So we go inside equation 2, and then we take this Laplace also out and then transform that one also I should know what we are going to get that one. That one, if you are following the trend, when it was t power n, we had it to be 1, we had it to be n over s we have to be n over s, now Laplace of t power n minus 1. And when we also transform Laplace of t n minus 1, we also going to be n minus 2 over s multiplied by Laplace of what? T power n minus 2 at this. N minus 1 over s multiplied by Laplace of t power n minus 2. So it means we will now going to transform this to a Laplace of t power n minus 2. Then that's what we can even give us n minus 2 over s Laplace of t power n minus 3. And to go on and on and on. So that's what we are having here. So if you also move on to transform Laplace of t n minus 3, that will also give us n minus 3 n minus 3 over s into bracket, or multiply by Laplace of t power n minus 4. So to go on and on and on. So we have equation 1, equation 2, equation 3 are going. But we can now check the link between all of them from equation 1 up to where we are going to end. There's some link between them. I'm sure you can identify it. So here we cannot even put 1 in place of 2. So now 2 into what? 1. Now inside the 1 we are having Laplace of t power n, and that y equal to n over s multiplied by Laplace of t power n minus 1. And t power n minus 1 we are now getting it as n minus 1 over s, now multiplied by t power n minus 2. So we are now getting this one. Now when we transform this one also gives us n minus 2 over s multiplied by Laplace of t power n minus 3. So we can now come and then put that 4 also into 3 here. And that will give us something. So let's move on. So we have equation 4 here. That's when we transform this one. That will give us equation 4. So let's go and put that one also inside equation 3. So put 4 into 3. And that will give us this n over s, n minus 1 over s, n minus 2 over s. Now Laplace of t power n minus 3. So now we go ahead, this also gives us n minus 3 power s, n minus 4 power s, and so on and so forth. n over s, n minus 1 over s, n minus 2 over s, n minus 3 over s, and so on. So which is a recursive. But you can see that if you are having n times n minus 1, we are taking the numerator, n times n minus 1 times n minus 2 times n minus 3 going, we can, it's like you are taking the factorial of a certain number. Because we have factorial n factorial to give you n minus 1, n minus 2, n minus 3 going up to 1. So this one now we can change this one as a factorial of n. So I said, but n factorial is given by n multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, n minus 4, up to 1. And the same result factorial is also 1. Hence, we cannot transform all this one to the numerator to what? N factorial. Therefore, we can simply say that Laplace of t power n will give us n factorial over s power n plus 1. N factorial over s power n plus 1. So that's the proof. So if you are transforming t power n, t to any power, a is the same as the power factorial over s power the power plus 1. That's how it is. So you see, when you find Laplace of f of t, we did this one, Laplace of f of t. So now apply this formula, we can see that our n is 1. So if n is 1, then we are now going to have 1 factorial all over s power 1 plus 1. And so that will give us 1 over s power 2. You got this. You got this over there when we change Laplace of t. So let's move ahead and see more examples. So let's find Laplace of t squared. Laplace of t squared. So with this, our n now is 2. So that we are now going to have 2 factorial over s power 2 plus 1. So it becomes 2 factorial over s power 3. And that 2 factorial is the same as 2. So it becomes 2 over s key. That one can here t power 5. Our n now is 5. So it becomes 5 factorial over s power 6. Because s power 5 plus 1. So when you simplify it, you know what you're going to get. Now f of 3, f of t equal to 3 now also give us what? Now we have done this one. This will give us 3 over x. 3 over x. So you can write this as, let's say, 3t power 0. 3t power 0 here. Therefore, to give us 0 factorial, 3 times 0 factorial over x. And 0 factorial, we are learning that it's 1. So it becomes 3 times 1 over x, which is the same as 3 over x. And we did Laplace of f of a constant, is the same as that. So that's what we have here. So if you know the transformation, we just change them straightforward. We don't prove them if you are solving the question, unless you are to prove. So it's better you know the transformation. So whenever a question is given and then you are just asked to change it to Laplace, if you know its transformation, just take it straight. And then you do what you are supposed to do. I hope it's okay now. Now let's move on to Laplace transforms of f of t equal to sinh, the hyperbolic functions, and f of t equal to cos 80. Now we have done that one for sinusoidal functions sin 80 and cos 80, whereby the Laplace transform of sin 80 is equal to a over a squared plus a squared. And that of cos 80 will also give us as s over s squared plus a squared. But let's see how we can also transform the hyperbolic functions. Good. So now we are having for the form of exponential function this sin 80 equal to, now if we want to transform this one into the exponential function, when you go back to Euler's formula, we are now having sin 80 equal to 1 over t into bracket exponential 80 minus exponential minus 80. That is sin. And the cos will also give us half into bracket expo 80 plus expo negative 80. So the difference between the two is sin is negative here and cos is positive. So in case I want to transform the sin 80 to Laplace, then we are Laplace sin 80 now becomes half. You know that we are not have to multiply this one by the transformer, which is exponential negative 80. So I multiply all this by exponential negative 80 dt. Integral from 0 to positive infinity. So we can now multiply or expand this. So multiply exponential negative st by exponential et, and the same thing by exponential negative 80 to get it. Now apply the law of indices for each integrand. We are not going to get this. So at this point you cannot integrate easily. So when you integrate this one, to give us negative exponential negative s minus a or t over s minus a, as we have it here, and I brought the negative outside here to multiply by the half. They do similar thing also here. We get this one also here. I won't waste my time there. So you cannot evaluate, but you can even bring you can just factorize the half out or just evaluate. So when we are having exponential here being or when t equal to what? Positive infinity, here will tend to 0. So it becomes 0 over st, which is 0. Minus when you put the 0 also there, this will become 1 over st. So we have 1 over st. Again, when you go to this side too, now this will also go away, and this will also becomes what? 1 over s plus t. So therefore we are now having it as 1 or half into bracket 1 over s minus a minus 1 over s plus a, half into bracket 1 minus s minus a from the first part. Now minus, don't forget we have negative sign here, so here become minus, or this minus, yeah, we have this minus there. So that's why we have that one also here. Oh no, yeah, there will be a negative here. So that we have it also here. So minus that. Now when we do the evaluation here, this will give us 0, all of them. Oh no, this will give us minus 1 over s minus a. And when we multiply that one by minus here, this negative sign goes away. When you go here, this also becomes, when you put infinity there, you get 0. So minus, when you put 0, they become minus half. So we have 1 over s plus a. That's what you can see here. So that brings this sign here. Check that. So now we cannot simplify. We can find the LCM between s minus a and s plus a, and s minus a, s plus a is also the same as the difference of 2 squares. So the same as s squared, the LCM will become x squared minus a squared. So when you take the LCM and they get simplified this, we are not going to get half into bracket x plus a minus s plus a. And when you simplify the whole top here, we are now going to get it as 2a, or half multiplied by 2a over s squared minus a squared. Therefore, when we simplify this one further, we have a over s squared minus a squared, because we have 2 over 2, and that will cancel this 2 here. So leaving here as a over s squared minus a squared. So Laplace of sin 80 is a over a squared minus s squared minus a squared. Good. So today we compare this one to the sinusoidal function sin 80. Only difference between them is here, for the sine is plus, but when you come to the hyperbolic sin, it is minus. That is the difference between the two. Good. So that's how we can now transform the singe to Laplace. And we can equally do so for that of the cosh. We can do the same thing for that of the cosh. So Laplace of singe at now is a over s squared minus a squared. Laplace of sine at is a over s squared plus a squared. So check the difference between the two. Similarly, we can also do the same thing for cosh at. And that as we did with the singe, that also becomes half exponential at plus exponential negative 80. So by going through as we did with the singe, we are now getting half into bracket integral from 0 to positive infinity of exponential 80 plus exponential negative 80 multiplied by the transformer with the exponential negative st dt. So by expanding and then simplify, we are not going to get this. Apply the law of integers, we get this. So by integrating each integrand, we are now going to have negative half into bracket exponential negative into bracket s minus a or t over s minus a. You should know why. That the limits are from 0 to positive infinity. Now minus, if we take the second one to, we have negative half into bracket exponential negative into bracket s plus a or t over s plus a. And the limits are 0 to positive infinity. So when evaluating the limits, we are now getting it as half into bracket 1 over s minus a plus 1 over s plus a. And taking the LCM as we did to the singe, then that becomes different of 2 squares. So in doing so, we are not going to get half into bracket s plus s minus a all over s squared minus a squared. So a goes away from the top here. A minus a is 0. Therefore, the numerator we are having it to be 2s over s squared minus a squared, all multiplied by half. And that will cancel the 2 there, leaving cosh at as s over s squared minus a squared. So this is the difference between the hyperbolic and the sinusoidal. Hyperbolic, we are having cos at as s over s squared plus a squared. But for hyperbolic, we are having cosh at as s over s squared minus a squared. The only difference between the two is the negative. Sinusoidal, we are having positive or plus in between the s squared and a squared. But for the hyperbolic, we are having negative between them. So these are only different between the transformation, how to transform the singe and the cosh, sine and cosine. So let's look at the examples. Transform ft or Laplace transform of ft equal to singe 2t. So here our a is 2. Therefore, we are not going to get a over s squared minus a squared. So it becomes 2 over s squared minus 2 squared. And that will give you 2 over s squared minus 4. So simple. Now we have Laplace of 3 cosh 5t. So I can bring the 3 out. So it becomes 3 Laplace of cosh 5t. It means here our a is 5. Our a is 5. Therefore, the cosh now is s over s squared minus a squared. So we have s over s squared minus 5 squared, all multiplied by the 3. And that will give me 3s over s squared minus 25. Now similarly, we have Laplace of 5 singe 3t. So as we did with the previous example, we can now bring the 5 out to get 5 Laplace of singe 3t. Our a now is 3. Therefore, we are not going to get 5 into bracket a, which is 3 now. So 3 over s squared minus 3 squared. I will simplify this. I will do the expansion to give us 15 over x squared minus 3 squared minus 9. Now last example, Laplace of 6 cos 4t also becomes 6 into bracket s over s squared minus 16. Cos 4 squared is 16. And that will give us 6s over s squared minus 16. So I think we have to end here and come and continue at our next meeting. So if you have any problem, just write it down when we meet. You can now bring your questions and we discuss over there. Thank you for coming. See you next time.